Hello everyone and welcome back. Today we're going to be talking about section 16.3 which continues the investigation of line integrals of vector fields that we talked about in 16.2, but now we're going to talk about some specific kinds of vector fields called conservative vector fields. So a vector field f is called conservative if it's the gradient of some scalar function. So that is, we can find some lowercase f such that the vector field capital F equals the gradient of lowercase f. And remember, the gradient is just the vector field of partial derivatives. Okay? And this lowercase f gets a special name. It's called a potential function. So why do we call these vector fields conservative? It has to do with conservation of energy. If you draw a conservative vector field, and then you draw any region where the conservative vector field is defined, you'll have the same amount going into that region as coming out. In other words, the vector field is pushing the same amount into the region that it's pushing out. Okay, so in this example, this would be a conservative vector field. I've outlined a region here, but I could draw any region, and the same amount would be going in and coming out. This vector field is not conservative. If you look at the region I've drawn, the vector field is pushing everything inside of this region. Nothing's coming out, so that's not conservative. Now that doesn't mean I might be able to draw a different region. For instance, if I draw a region here where the same amounts might be coming in and going out, it's still not conservative because that has to be true for every single region, that the same amount's going in and coming out. So that's why we call these things conservative. Okay? Why do we care about conservative vector fields? Well, before we get to why we care about conservative vector fields, they have very nice properties. Let's review some Calc 1. So in Calc 1, kind of the biggest result, everything was leading up to the fundamental theorem of calculus. That's if you had a continuous function on a closed interval, there were two results. First, if you define this function as an integral, so x is a variable, you're always integrating up to whatever the variable is, then the derivative of this integral function is whatever function you're integrating. G prime is equal to f. The second result, which is the one we use more, and what we're going to build on today, is actually a definition of how we evaluate definite integrals, right? If I integrate some function, lowercase f, it's equal to an antiderivative of that lowercase f at the endpoints, at the bounds of integration. So here we have capital F of b minus capital F of a, where capital F prime has to equal lowercase f. Okay? So now we're going to build on a similar result. It's called the fundamental theorem of line integrals. So this says let C be a smooth curve, and it can be parameterized by R of t, where t goes from a to b, and let f be a differentiable multivariable function whose gradient is continuous on C, that if I want to take the line integral of the gradient, then I can evaluate that as just the function itself before I took the gradient at the endpoints of my curve. So R of b is where I stopped the curve, R of a is where I started the curve, so it's just f of the endpoint minus f of the starting point. So this I have to have a gradient field for this to be true, so it has to be a conservative vector field, right? This is only true for conservative vector fields. So if I have a conservative vector field, I can use this result. But if I just give you a vector field, how can we tell it's conservative? Okay, this is not an easy question, and it's going to take a while to answer. First, let's just suppose that we have a conservative vector field. If we have, and let's start with a vector field of two dimensions. So we have two component functions. If this is conservative, then we know there exists some potential function such that this vector field is the gradient of this potential function. So what that means is that this first component function is actually the partial derivative of our potential function with respect to x. And this second component function is actually the partial derivative of our potential function with respect to y. Okay? Now, if in addition p and q are differentiable, they have continuous partial derivatives, then I can take a partial derivative of p with respect to y, and that's really going to be a second order partial with respect to my potential function. since p itself is already the first order partial derivative. So if I take a partial derivative of p with respect to y, what I'm really doing is taking the second order partial of f, the mixed partial. First I take the derivative with respect to x, that gives me p. Then I'm taking a partial derivative with respect to y. Well, if these partial derivatives are continuous, if you remember back to section 14.3, we had Clairaut's theorem that says if you have a mixed partial derivative and these things are continuous, you can switch the order of integration, which means that this second order partial is equal to the second order partial if I take the partial derivative with respect to y first, and then I take the partial derivative with respect to x. Well, the partial derivative of f with respect to y, that's q. So this is really equal to the partial derivative of q with respect to x. So that means if I have a two-dimensional conservative vector field whose component functions have continuous partial derivatives, then the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. Okay, and that's what is summarized in this next theorem. So we have to have that this is conservative. These component functions have continuous first-order partial derivatives throughout some domain D. Then in D, we have this relationship. The partial derivative of the first component with respect to the second variable is equal to the partial derivative of the second component with respect to the first variable. So you can see things kind of correspond diagonally. This is the first component, this is the first variable. This is the second component, this is the second variable. So this was for a two-dimensional vector field. In 3 dimensions, things get a little more involved, right? So in 3D, now we have a vector field of 3 component functions. I'm assuming that this is conservative, and I'm assuming that each one of these component functions have continuous partial derivatives. Then there are 3 relationships that are satisfied. This is the same relationship that we had in 2 dimensions. Now I also have that the partial derivative of p with respect to z is equal to the partial derivative of r with respect to x, and the partial derivative of q with respect to z is equal to the partial derivative of r with respect to y. And these 2 relationships can be proven the same way that this relationship was proven. You can rewrite these in terms of second order derivatives of your potential functions, so second order mixed partial derivatives of f, and then if they're continuous, we use Clairaut's theorem to switch the order of integration, which gives us this equality. Also notice that for these 2 relationships, we also have this diagonal correspondence. P is the first component, x is the first variable, r is the third component, z is the third variable. Similarly, q is the second component, y is the second variable, r is the third component, z is the third variable. So that's one way to remember what these 3 relationships are for 3-dimensional vector fields. Now, some of you might notice I haven't even begun to answer this question. This question is, if I just give you a vector field, how do we tell if it's conservative? But for everything I've written here, I started by assuming I had a conservative vector field. I want to go the other way. Are these relationships enough to tell me that a vector field is conservative in 3 dimensions? Is this enough to tell me that a vector field is conservative in 2 dimensions? Not quite. We need to assume some more definitions. So we need to go through some more technical details. And this will take just a minute, and some of this might be pretty abstract, so just bear with me. The first definition we need is the definition of an open region. So we call a region D open if for every point in D we can find a disk centered at that point that's also contained in D. So what is this saying? Let's do an example here. Here I have some large disk that does not contain the boundary. So the boundary here is dotted, it's not included. I pick a couple points. Here's a point here. I draw a smaller red disk. It's contained inside of my larger region D. If I pick this point here, I can always find a smaller red disk that's contained in this D, and that's always going to be true. This is an open region. So no matter what point I pick, I can always find a disk around that point that's contained in the region. This example is not open, so what have I drawn here? Here's a region that comes to a cusp on the boundary, and if I pick the point on the end of that cusp and I try to draw a disk containing that point, doesn't matter how large or small I make this disk, there are always going to be points in this disk that are outside of my region. And in fact, I don't have to choose this cusp. Anytime you have a region that contains the boundary, I could pick any point on this boundary. Let's say I'm right here on the boundary. I try to draw a disk around that point. Some of that disk is going to be in my region. Some of that disk is going to be outside of my region. So if I include the boundary, it's automatically not open. That's why we've eliminated the boundary here. A third example, I have this open disk before, and I'm including a point outside of that disk. So my region D, I'm defining to be this open disk, plus one more point that's outside. This is not open. This component itself is open, but this point, if I draw a disk around it, I draw any disk around it, it's not contained in here. It's kind of an isolated point, so this can't be open. And again, the region is this plus 1 point, so that's not open. That's the most technical definition we'll go through, and it's not terribly important. If you're confused at this point, that's okay. It's not going to come up too much, but it is a word that gets used, so it's important that we define it. The next definition is a little bit easier to understand. A region is connected if you can pick any 2 points and draw a simple curve, so a curve that doesn't intersect itself. You can draw a simple curve between those 2 points without leaving the region. And in 2 dimensions, well, in any dimension, what this means is that the region is only one piece. So if you look here, I have this annulus. I pick any 2 points, let's say these 2 points. I can draw a curve between them and stay in my region, in this washer region. And there are infinitely many curves I can choose. But if I pick this region with these 2 pieces, and I pick a point in each piece, I can't draw a curve between these 2 points without leaving my region. I have to go through this empty space here that's not in my region. So this is not connected. So connected just basically means one piece. The last definition is simply connected. A region D is simply connected if you can draw any loop in that region and shrink it down to a point without leaving the region. So here we have a simply connected region. I draw any loop I want. I can shrink this loop down to a point and stay in my region. Here's an example that's not simply connected. So this kind of looks like a mask. It's got 2 holes in it. If I draw this loop here, I can't shrink this down to a point without having to cross through this hole. And so that means if I cross through this hole, I'm leaving my domain. That's not simply connected. And I could also draw a loop over here where I'd have to leave the domain to shrink it down to a point. I could draw lots of other loops that I can shrink down to a point, but if I can find one I can't shrink down to a point, it's not simply connected. In 2 dimensions, simply connected means there are no holes, right? So that's pretty easy to see. This has holes, it can't be simply connected. This doesn't have holes, it is simply connected. In 3D, things get more complicated. For instance, a torus, a donut shape, that's not simply connected in 3D, but you can have solids with cavities. Those are simply connected. For instance, think of a peanut M&M without the peanut, so just the shell and the chocolate. I could draw a loop inside of that region and still shrink that loop down to a point. Any loop I draw in that region, I could shrink down to a point because I can always find some way to go around that cavity, that empty point in the middle. So I just say that to say that these ideas get more complicated when we start thinking in 3 dimensions. We're not going to have to deal with things in the problems that we do that involve these technicalities. But since we're using these words, we should define them. So now we finally get to answer our question with this theorem. Let F be a 3-dimensional vector field defined on an open, simply connected region D. If the components of that vector field all have continuous first-order partial derivatives on D, and these 3 relationships hold, these are the 3 relationships we talked about earlier throughout D, then F is conservative. So we know if F is conservative and has continuous partial derivatives, then these 3 relationships hold. If we want the reverse to be true, we have to assume that we're on an open, simply connected region. If we're not on an open, simply connected region, these might still hold, but F might not be conservative. So that's something to keep in mind. So that's for a three-dimensional vector field. In 2 dimensions, it's much easier, right? We still need to be on an open, simply connected region, but we only have one relationship to check instead of 3. So let's end with a quick example. Is this vector field 2xy, x squared minus y conservative? So first, let's check our assumptions. What region are we talking about? Well, F is defined on all of R2, so basically the xy plane, any x and y. R2, the xy plane, it is open and it is simply connected. I'm not going to go into details, but that's true. I take a partial derivative of the first component with respect to y, I get 2x, and this is continuous. It's continuous in the xy plane. I take a partial derivative of the second component with respect to x, I get 2x. This is continuous. These two are equal, F is conservative. Now most of the time, this is the property we check, just this fourth one. Are these two partial derivatives equal to each other? And we say that's enough, F is conservative. And we forget about checking the assumptions on our region. Is it open and simply connected? And are these things continuous? And that's going to be okay for the most part, right? I'm not going to require that you check all of these things. Just know that for some of the other results that we're going to come up with for conservative vector fields, if something goes wrong, and you're pretty sure that all of your arithmetic is correct, all of the calculations you've done are correct, go back and make sure you check these assumptions. You might not actually have a conservative vector field, even if this relationship holds. It's possible. So what we've done is given a vector field, now you can figure out if this is conservative or not. In the next video, we'll see how we can actually find the potential function given its gradient, its conservative vector field.